ever stop to think about how the words you type on a screen just get understood by your computer? It kind of feels like magic, right? But it's not. It's all about translation. And today, we're going to crack the code that lets us speak a computer's native language. You see, at its heart, this is a classic language barrier. We think and talk in one way, but machines, they operate in a totally different world. So the big question is, how do we bridge that gap? How do we get fluent in their language? All right, so to kick things off, we've got to get a handle on the biggest difference between us, how we count. Think of it like a translation problem, where the translator is math. So, on one hand, you've got our world. We use the decimal system. That means we have 10 digits, 0 all the way up to 9, to build every number we can imagine. But on the other hand, you have the computer's world, binary. It's way simpler, just 2 digits, 0 and 1. That's it. Why? Well, because a computer thinks in terms of off and on, like a light switch, and that's exactly what 0 and 1 represent. Every single thing a computer does, it all boils down to long, long strings of these two numbers. Now, the concept that kind of glues all this together is called the base, and it's super simple. A system space is just how many unique digits it has to work with. So for us, since we use 10 digits, we're base 10. For a computer with only 2 digits, it's base 2. Getting this one little idea is pretty much the first key to unlocking this whole translation thing. Okay, so let's get into how this translation actually works. We're going to look at the direct, step-by-step way to go from our base 10 language to the computer's base 2. This is really the nuts and bolts of it all. So to go from our language to the computer's, we use something called the division method. It's actually pretty straightforward. You just take your number, let's say 37, and you divide it by 2. Then you write down the remainder. It's always going to be either 0 or 1, right? You keep doing that, dividing the result by 2 again and again until you can't divide anymore. And here's the trick. You take all those remainders you wrote down and just read them in reverse order. Let's try it with our number, 37. And there you have it. You follow those steps and our number 37 becomes 100101 in binary. That right there is exactly how a computer sees the number 37. Okay, but what about going the other way? How do we translate back? Well, for that, we use the positional method, and this one is all about place value. You know how in our numbers you have the ones place, the tens place, the hundreds place? It's the same idea, but with powers of 2. You start from the right with 2 to the power of 0, then 2 to the power of 1, and so on. All you do is multiply each binary digit by its position's value, and then just add it all up. Now, that method works perfectly, but it can get a little clunky, especially when you're dealing with really big numbers. Programmers, engineers, they needed a faster way, a shorthand. And that brings us to the real game changer in all of this. Here's the thing. Binary is perfect for computers, but for us humans, it's kind of a nightmare. You get these massive, long strings of ones and zeros that are just impossible to read without making a mistake. So yeah, there had to be a better way for the people who look at this stuff all day long. And that solution, it's called hexadecimal, or hex for short. It's a base 16 system, which means, you guessed it, it uses 16 different symbols. It uses our normal 0 through 9, and then for the numbers 10 through 15, it just uses the letters A through F. The whole reason hex exists is to be a super compact, human-friendly way to represent those giant strings of binary. Okay, this is the magic trick right here. This is what makes hexadecimal so incredibly useful. Each and every hex digit corresponds perfectly to a group of exactly 4 binary digits. A little group that's sometimes called a nibble. Cute, right? But seriously, this clean 1 to 4 relationship, that's the secret sauce. That's the shortcut. And this is basically the cheat sheet. It's the decoder key that makes it all work. As you can see, every single hex symbol, from 0 all the way to F, has its own unique 4-digit binary code. There's no complicated math here, it's just a simple swap. A is always 1010, F is always 111111. You just look it up. So, turning a huge binary number into a neat little hex number is ridiculously easy. Seriously, you start from the right side of the binary string and you just chop it up into groups of 4. If that last group on the far left is a little short, no big deal. You just add some zeros to the front to fill it out. Then you just swap each little group for its hex symbol from that chart we just looked at. That's it. So, take a look at this binary number. 1101011111. It looks like a mess, right? It's just intimidating. But once you group it up and do the swap, it becomes the clean, simple hex number 1AF. So much easier to read and remember, isn't it? All right, let's put it all together now. We're going to take one number and follow it on its entire journey, from our world into the computer's world, and finally into that slick programmer's shorthand. And our number for this little trip is going to be 50, just a nice, simple, everyday number. Let's watch how it completely transforms as it moves through these different systems. Okay, step 1, we translate our decimal 50 into the computer's language. So we do that division by 2 thing, we track the remainders, and boom, the number 50 becomes the binary string 110010. And now for that programmer's shortcut. We take our binary result, 11010, we group it into 4s from the right. That gives us 2 chunks, 11 and 0010. That first chunk is too short, so we add 2 zeros to the front, making it 0011. Now we just look them up on our chart. 0011 is the number 3, and 0010 is the number 2. You stick those two together, and you get our final result, 32 in hexadecimal. So what does this all mean? It means these are just 3 different ways of saying the exact same thing. Our everyday 50 is identical to the computer's 110010, which is identical to the programmer's clean and simple 32. It's 3 languages, but just one single meaning. And really, that's the big takeaway here. Hexadecimal isn't just some other weird number system. It is the essential bridge. It's the human-friendly tool that lets people work quickly and accurately inside the computer's native world of ones and zeros. Kind of makes you wonder, doesn't it? I mean, this is just one layer of translation. What other amazing shortcuts, what other clever little linguistic bridges are hiding deep inside the technology that we rely on every single day? Definitely something to think about.